Now let's go ahead and take a look what happens when we rotate around the y-axis. So here we have y equals e to the x, y equals x minus 1 squared, and the line x equals 1. Now you'll notice in these instructions it says to set up but don't integrate. So what does that mean? Don't evaluate. Don't actually find the value of that integral. An expression in terms of a single variable for the volume of the solid generated when r is revolved around the y-axis. So e to the x is exponential. Its y-intercept is at 0, 1. And x minus 1 squared, if you recall your parent function transformations, a minus 1 inside with the x will shift it to the right one. Sorry, I drew it a little too straight. It's this bottom one here. And the line x equals 1. So you'll notice I want to rotate this piece around the y-axis. So let me go ahead and draw the mirror image of it on the other side. So just imagine rotating this piece around the y-axis. So you would have sort of strange gap in here, and the top part would come around like this. So let's go ahead and draw our slices first. Let me use a different color. Because we are rotating around the y-axis, our slices now need to be horizontal, and then we'll add up all those slices, all those horizontal slices together and make it an integral. So if I were to draw the slice over here, similar to before, I would need to find the top y minus the bottom y, or in other words, the right y minus left y. However, because we have horizontal slices, this is now going to be changed with respect to y, not change with respect to x. So I need to take these two equations and I actually need to solve for x. So how do I undo an e? Take a natural log of both sides, or if you recall, just change this into its logarithmic form. So you would get natural log of y equals x. So that one's not too bad. This one, take a square root of both sides to undo the squared, and then add 1. So remember your radical rules. You cannot add a 1 inside with the radical, so it's just going to sit right next to it. So if it helps to figure out which one's the top y, the bottom y, the outside radius minus the inside radius, you can shift your paper this direction. You can see the outside radius would be whatever curve was out here, and your inside radius will be whatever curve is in here. So now you'll notice this one's kind of funny. The outside curve is always 1. There's always x equals 1. So that's always going to be your outside curve. However, your inside curve actually changes depending on where you draw your horizontal slice. Up until 1, your outside curve is the x minus 1 squared curve. However, if you were to draw a slice up here, you'll notice the curve has a different inside radius. The outside radius is still a 1. The inside radius will now be the e to the x curve, so in other words, the natural log of y. So for this top part, we have natural log of y, but for the bottom slices, our inside radius is the square root of y plus 1. So we actually need to set up two different integrals in order to show this rotation. So recall that we need to find our boundaries going from the y values. So from 0 up until 1, we have these slices. So our outside radius was 1. Our inside radius is square root of y plus 1 squared. And this is all with respect to y. So that just gives me the volume from 0 up to 1. Now from 1 up to this intersection point up here, we would need to find the boundaries and the y values. So the question is, what happens when I plug in 1 into the e to the x curve? So e to the 1 power would be just the value of e, so 2.718. So my next slices are going from 1 to e. Again, now I'm going to use these slices, but again, my outside radius is still 1, my inside radius is natural log of y. And there you have it. This problem just asked us to set up, but don't integrate. So this is actually your final answer. Again, this is part of a free response question, so don't even bother multiplying anything out. Just leave it all like this. Next example, it says example 5, should be example 4. We have the first quadrant enclosed by the graph of y equals square root of x, 6x plus 4, the line y equals 2x, and the y-axis set up, but don't integrate. An integral expression in terms of a single variable for the volume of the solid generated when r is revolved around the y-axis. So you'll notice this says in terms of a single variable. If you continue to take calculus in college, you will learn about something called multivariable calculus, which personally I found was a lot of fun. But here in AB calculus, you only learn single variables, so it's what you've been doing, right? You either have a y or you have an x. You don't have both. So if you'd like, go ahead, pause the video if you want to go ahead and try it on your own. If you don't feel confident, just go ahead and keep playing. So we are in the first quadrant. I'd like to know what this square root graph will look like. So if I plug in 0 in for x to find the y-intercept, I see my y-intercept is at 2. And square root has sort of curve shaped like this, like an eyebrow. And then also the line y equals 2x. So I know they will eventually meet at some point. So how can I find that point? If you'd like, you can go ahead and set them equal to each other. You would need to square both sides to get rid of that square root. So if you square 2x, that means 2x times 2x, which is 4x squared. So then here you would move all the terms over to the other side, set it equal to 0, factor, and then you would find that one of the intersection points is at 2. And when you plug into either of the equations, you get a 4. We would like to rotate this around the y-axis, so let's draw what this will look like. So again, it's kind of this strange upside down cone shape. However, the inside of it is free. There's a gap in here on the inside. So this time we do need to use horizontal slices. And I'm sure you've noticed, depending on where you draw your horizontal slice, it could go from line to line, or it could go from line up to the square root curve. So it's a little strange where our slice is. So again, similar to last problem, we do need to set up two integrals. So let's take a look at this top slice up here. If I look at this top horizontal slice, my outer radius, in other words, my top y, so again, if you need help seeing that, your top y will be this outside one, and then your inside radius will be the one to the left, or in other words, the one on the bottom. So in order to see what those are, we do need to solve for x in both equations. Well, this one has less steps, a little more straightforward. The other one, you do need to square both sides. Subtract the 4. And then divide by 6. So here our outside radius was the line. So that means y over 2 is my outside radius. My inside radius will be the y squared minus 4 over 6. So these are all in terms of y values. So here you'll notice when you draw your slice, a radius is just half of this. So we're really just really just looking from here to here, because if we looked at the whole slice, we'd be looking at the diameter. So here my outside slice is y over 2 squared. My inside slice is just the y-axis, so in other words, it's just 0. Okay, so we're going to set up two integrals. Again, my boundaries need to be on the y-axis. So from 0 up to 2, I just have the slices that go from the line to the the y-axis. And now for the other slices, you see we have an outer minus inner. And again, if you forgot your boundaries, they need to be on the y-axis. So we're going to go from where we left off at 2, and we have to go up to 4. We found the 4 by plugging in the 2 into the equations. And similar to the last problem, we don't actually have to evaluate, so that would be your final answer. Do not bother, oops, sorry, I forgot to square. Do not bother multiplying any of these things out. If it's free response, they will accept your answer like that. All right, example number 6. Go ahead, pause here. When you click play, I'll go over it. So this one, it gives you a graph, which is kind of nice. We just need to find the outside radius and the inside radius. So you'll notice we need to revolve around the x-axis. So if it helps you to draw a picture, it would be almost donut shaped, I suppose. A very strange donut that came together in the middle of the hole. So we need to draw a slice. So here my top y, my outside radius, is y equals 4. My inside radius is x squared. And you'll notice no matter where I draw that slice, it's all going to be the same, unlike the previous problems where depending on where we drew the slice, it could have different outside and inside radii. So using the formula, we just need to figure out my x values. So because I'm going from the second quadrant all the way to the first quadrant, I do need to go from the negative x's all the way to the positive x's. So in order to find that, I would set x squared equal to 4. And to find where they intersect, an x would have to intersect at 2 and negative 2. So those are my boundaries. My outside radius is 4. My inside radius is x squared. This one, you can use a calculator. So go ahead, grab your calculator. Just for simplicity's sake, I'm going to go ahead and multiply out the x squared and just say it's x to the 4th. Alright, so you should get 160.850 if you're rounding to 3 decimal spots like College Board wants you to. Last problem, go ahead, click pause again, And when you click play, I'll go over it. Alright, so again we have another region that needs to be revolved around the y-axis. So cube root of x kind of looks like a square root, however it grows a little bit slower. X over 4 is a line. And you notice it says specifically that it lies in the first quadrant. So we need to rotate it about the line about the x-axis. So it looks something like this when you rotate it. Here you go. Here you go. This one I actually do have a 3D graphic image, well, 3D image on paper. This is what it looks like to help you visualize. If I were to cut a slice here, this is what the washer would look like. So when we need to find the radius, we need to find from here to here. And this time you'll notice no matter where you draw that slice, the outside radius will always be the line. The inside radius will always be the cube root of x. So here I only need to just find the outside radius, inside radius once, and be done. Okay, so a couple things we need to do first. We need to solve for x. Again, why do we need to do that? Because I'm going to draw horizontal slices here, and horizontal slices means that we need to look at the change in y values. So all those washers are horizontal. So if I find the find the area of each one, then I can find the volume of this by adding them all up using the integral. So my inside radius is y cubed. My outside radius is 4y. I do need to find where they intersect. You notice this problem does not say calculator active, so this does require some algebra knowledge in order to find where they intersect, or if you just want to take a guess, you might be able to guess what values will work here and here. So first off, if you cube both sides, you would get x cubed over 64. So we rarely try to solve cubics, but we can do something similar to parabolas, where you try to solve for 0. I notice here that an x is common in both of them, and then if you don't recognize this as difference of squares, you could still do x box to this. And so you find that these two graphs intersect at 0, 8, and negative 8. So because we're in the first quadrant, we only care about the 0 and the 8. So in order to find the y value, plug it into either equation, you will get 2 both times. Alright, so using my formula, 0 to 2, 4y squared minus y cubed squared dy. So this one again is not calculator active. So if you want to practice finding your antiderivatives, you can go ahead and do that. When you do that, you will get 512 pi over 21, or in other words, you can get 76.595. Now, of course, if this were a free response question, you can simply input the values and you don't have to simplify any further. So let me show you my work. Here you find the antiderivatives and then you plug in 0 and 2. So actually I went ahead and found common denominator. You can see I messed up a little, but honestly stop right here. For College Board, you don't need to simplify beyond this. You would just circle this and this would be your final answer.